to us about eigenvalue bounds for the mixed Steklov problem. So Asma, the floor is yours, and thank you very much for speaking here.
Thank you, Jean, for having me. First of all, I'd like to thank Alexandra and Jean for organizing such a nice series of virtual seminar. So today I'm going to talk about eigenvalue bound for mixed Steklov problem. And this series of talk, we've seen several talk on the eigenvalue bound for the Steklov problem and the discussion on some sharpness of some of the bounds. And during this talk, we will review some of those results, but the focus will be on the interplay between the Steklov-Dirichlet and the Steklov-Neumann problem. So this talk is joint work with Teresa Arias-Marco, Emily Dryden, Caroline Gordon, Ali Ray, and Liz Stanhope. I think some of my colleagues are here present at the moment. So let's first start with the setting, and then we review some of the previous results, and then we get to the main point of discussion. So during this talk, unless I mention, the setting is we are in the two-dimensional setting, and the underlying surface is always orientable. So here, omega is a domain with Lipschitz boundary in a complete Riemannian surface. So let me first recall the Steklov eigenvalue problem, which is on the left. So here the spectral data is on the boundary, and the normal derivative of u is proportional to the value of u on omega, and it's harmonic inside. And the eigenvalue of a Steklov problem is a discrete sequence of non-negative number, and each of them has finite multiplicity. The first eigenvalue is 0, corresponding to the constant function, and we start our numeration with 0. So this we need to keep in mind for later. So on the right, we have a Steklov-Neumann problem. So here, our boundary, we make a partition to two parts. One, we put Neumann boundary condition, and we denote it by dn of omega, and ds, where we put the Steklov condition. And to distinguish like which eigenvalue problem we are talking, we put Sn, stand for Steklov-Neumann eigenvalue. And again, we start our numeration with 0. So we also talk about the Steklov-Dirichlet problem. So here, again, on one part of the boundary, we put the Dirichlet condition, and on the S of omega, we have a Steklov condition. And here, our numeration starts with 1 because we don't have a 0 eigenvalue. So the sigma 1 is the first eigenvalue of a Steklov-Dirichlet problem. So another problem that we need to mention, and going back to the Steklov-Neumann, it's actually the weighted Steklov problem, because Steklov-Neumann in many cases is a special case of weighted Steklov problem. So what is weighted Steklov problem? We put weight here as a multiple of u, and this weight rho is a non-negative function in L infinity of the boundary of omega. And again, we have this discrete sequence of eigenvalues. And for example, in this picture, so here the blue part, I hope that it's visible. So the blue part represents the Neumann eigenvalue problem, where we put the Neumann condition, and the black part, we put the Steklov. So if I take rho to be 1 on the Steklov part of the boundary and 0 on the Neumann part of the boundary, so this is a valid weight, and we get the Steklov-Neumann problem as a special case of weighted Steklov problem. So here I like to mention two remarks. The first is that when weight is strictly positive and the boundary is smooth, this is equivalent to the actual Steklov problem, because if we define in two-dimensional, one important fact is that the harmonicity is conformal invariant. So if we take a metric in the conformal class of G, such that then the boundary is equal to rho g. Then if we look at the Steklov problem, with if we write the Steklov eigenvalue problem for this metric G tilde, then these two eigenvalue problems are equivalent. So putting a smooth, a strict positive weight doesn't change the problem to the weighted. So the weighted problem is interesting when the boundary is non-smooth and we allow a non-negative weight. So mentioning this conformal invariant, I like to give another remark is that, so if we don't change the metric on the boundary, this and metric G tilde is in the conformal class of metric G, then the Steklov eigenvalues are the same. So we can make the same argument as I make here, or we can look at the variational characterization of eigenvalue, and we see that the numerator is conformally invariant, and if we don't touch the boundary, then the eigenvalues doesn't change. And the same is true for the Steklov-Neumann eigenvalue and the Steklov-Dirichlet eigenvalue. Here we see the variational characterization for the Steklov-Neumann eigenvalue. For the Steklov-Dirichlet will be the same. So here in the denominator, we only integrate over the Steklov part of the boundary, and if we don't touch the metric here and we change the metric conformally, eigenvalues does not change. So this is kind of a basic fact and the setting that we will use again. So I forget to mention, if at any point you have any question, or even in the introduction, if I'm too fast, please stop me and ask question, because we will use this idea later on. Okay, so now I want to give you like kind of two motivation or one physical interpretation and one geometric interpretation to motivate the mixed eigenvalue problem, mixed Steklov eigenvalue problem. And these two settings that we are interested in, so actually we can see it in these two pictures. So the first is a sloshing. So here we put the Steklov, so the sloshing problem, if the Steklov part is flat, so for example, if you have a mug and the part of the coffee on it that sloshes, this is satisfies the Steklov condition, and the rest is Neumann. So for a sloshing problem, the Steklov part is flat or is a geodesic. And the second example is for domain with reflection symmetry. So here M is our domain, and tau, this axis is so M is symmetric with respect to this axis. And here, if we name omega, the first half of that, so all of so if we consider the Steklov eigenvalue problem on, on M. So then the sigma k of M is, we can correspond a basis of eigenfunction to sigma k of M, such that each of fk is either symmetric or anti-symmetric with respect to this axis. And if we restrict this eigenfunction to omega, then we get either it corresponds, this eigenfunction, if it's symmetric, corresponds to the Steklov-Neumann eigenvalues of omega, and if it's anti-symmetric, it corresponds to a Steklov-Dirichlet of omega. So basically, the Steklov eigenvalues of M is a disjoint union of these two eigenvalue problem. Okay, so this is kind of the background and basic definition that we need throughout the talk. And now we want to review some of the known upper bound for the Steklov problem and for weighted Steklov problem. So any questions so far? Okay, so the first upper bound is Weinstock inequality. So here the setting is that omega is a simply connected bounded domain in R2, and we have a non-negative weight. The boundary is Lipschitz, and Weinstock proved that the normalized, if we normalize the sigma 1 but by the weighted length of the boundary, then the upper bound is 2 pi, and this is actually equal to the sigma 1 of d, which is 1 times the perimeter of the unit disk, which is 2 pi. And the equality is attained when omega, when omega is the disk, and this is an if and only if statement. And Hirsch-Paine-Schiffer result extend the Weinstock inequality to higher order eigenvalues. And also, it's interesting that this 2 pi k is a sharp upper bound. So Girard and Poltrovich, they showed that this 2 pi k is sharp, and the family that they construct, it's for sigma k, they consider k overlapping disk. So here this distance between this overlapping part, you can think of itself length epsilon, and when epsilon goes to 0, they converge to the disjoint union of disk, and this family, the limit of sigma normalized sigma k is 2 pi k. So we come back to this nice example later. Girard and Poltrovich also actually extend this result when we have for surfaces with non-trivial topology. So if we have genus gamma and B boundary component, then they prove that we have this upper bound for the weighted Steklov problem. And I like to emphasize that when I say weighted, it's always non-negative. Of course, it's not identically 0, it's non-negative, and it's include the Steklov-Neumann problem. So all of these sharp bounds that we have, it's also true for a Steklov-Neumann. And this bound here, it's improved by Karpukhin. So the only price that here we give, it's the fact that the boundary should be smooth. And if we put weight should be strictly positive, which means that we end up at the setting of unweighted Steklov problem. And we can ask if we can extend to the Lipschitz domain with non-negative weight. The answer is yes. So there is two ways we can think of: either go through the proof and see if we can adapt. And actually the proof based on the extension of Hirsch-Paine-Schiffer result for and using a Steklov eigenvalue problem and differential forms. So it might sound a little bit technical to adapt this proof for mixed Steklov problem and forms. But there is easier way to do that, and actually this is thanks to a geometric lemma by Bukur and Naon. So some of you might remember Bukur talk that he uses this lemma to prove the instability of Weinstock inequality. So here, what this lemma basically says, so I don't want to go to all of the detail, it says that if we have a Lipschitz domain and the family of domain omega epsilon that converge to omega in a nice way uniformly, so, and by uniformly means that this sequence are uniformly Lipschitz as a domain, or satisfies uniform cone condition. If you don't know the exact definition, it doesn't matter at the moment, but plus this converges to omega in some nice, not very strong sense in Hausdorff complement topology. And also if we have a sequence of weight that converges in weak star sense, then the Steklov eigenvalues of omega epsilon with weight rho epsilon converges to Steklov eigenvalues of omega with weight rho. So now as a corollary, so if we, then it says that if we have a topological upper bound for a Steklov problem on a smooth domain, then applying this lemma, we can obtain it for non-negative weight and for Lipschitz domain. So this is a corollary, just using Bukur unknown lemma. So we again, we are in the previous setting. So omega is orientable surface of genus gamma with B boundary component. And now we assume that it's Lipschitz and we have a non-negative weight. Then we have Karpukhin upper bound for this family applying that lemma. And B star here is the number of boundary component on which rho is supported. So we don't need to count all of the boundary component, and the reason it's simple. So if this is omega, so maybe I use color code. So if the black is the Steklov part and blue is the Neumann part, if we have some Neumann and the Steklov part, so this is the n of omega, or by Neumann part, I mean where the rho vanishes, and this is the S of omega. So the first thing we do, we cap this purely Neumann, or the boundary component on which rho vanishes. We cap it by a disk, so we get a domain omega prime, which contains omega, and then by monotonicity of eigenvalues, we know that sigma k of omega prime is bigger or equal than sigma k of omega. So I should have put rho. And then we prove the upper bound for this one. So for this one, what we do, so the first step is cap it with a disk, as we saw in this picture. And the second is find the sequence of a smooth domain and the sequence of a strictly positive weight such that it approaches the rho in a big star sense. So actually, we want a sequence that satisfies all of the hypotheses of this theorem or this lemma. And then we pass to the limit, because the upper bound is topological and doesn't see any this procedure, or doesn't see this rho, then we get this upper bound. Okay, any questions so far? So I'd like to add that when k is a small, k is a 1 or 2, so we had this Weinstock inequality for k equal 1, which was sharp. And if we don't have any topological restriction, then it was a nice result by Karpukhin and Stern. And for those that attended a Stern talk, so the application of their result for a Steklov problem was that for k equal 1 and 2, the weighted Steklov problem, if you normalize it by the weighted length of the boundary, is bounded above by this conformal quantity, which is the supremum. This is the, so omega is a domain in M, a closed Riemannian manifold. So here we need to assume that M is closed manifold. So here it's a Laplace eigenvalue, normalize it by area. And we know that this bound also is sharp due to the result of Girouard and Lagacé. And there are also previous results by Kokarev that prove this topological upper bound when k is 1. So actually, when gamma is 0 and k is 1, so the bound 8 pi that we have here, and this quantity when gamma is 0 also is 8 pi. This is sharp. So this quantity we know the value only for in a few cases, and amongst those is when gamma is 0. And in general, for higher k, even though we have this nice bound, we know that we can always get a topological upper bound. But here, this A and B are implicit constant. We can estimate A and B, and they are large numbers. So this is a good bound when the number of boundary component goes to infinity. Otherwise, the other bound is more explicit and precise. Okay, so far, this is the results that we kind of know about the weighted Steklov problem. So all of the results so far is true for weighted Steklov problem, and in particular for Steklov-Neumann, and the sharpness also holds. So now the question is that, can we improve those results for the mixed Steklov problem?
Sorry, Asma.
Yeah.
Before you go on, there was a question in chat relating to those convergence results, and I think it would be good to look at it before going on.
Okay. Are there estimates for this convergence uniform in the number of which convergence?
So I think this refers to the convergence of the
Bukur-Naon.
Yeah, exactly. So is this uniform in the eigenvalue index?
Is it uniform in the eigenvalues? In the number of K, I think probably not.
I mean, that was my question. I mean, some estimates which are uniform.
So you mean here the resolvent converge to each other as an operator? I think not probably in that case. So I know this kind of, so for example, for Neumann eigenvalue problem, it is can, with some similar condition, it's a convergence of resolvent under some, which is uniform in K, but I don't know if Doreen is here to comment.
Can I say something? It's Alex.
Yeah.
I think the answer is no, because otherwise you could transfer some asymptotics behavior for smooth domain to domains with corners, and we know it's not going through. You know, the fine asymptotics for smooth domains contains information that is not true for domains that has a corner, for instance. And I think if the convergence was uniform, it would lead to better asymptotics for domains with corners.
Yeah. So and also Naon says that, so he doesn't believe that it's uniform in K. Yeah, the proof, it's for every K. So it's a kind of proving upper and lower semi-continuity. So it's not like the convergence of resolvent. So I don't think, yeah.
And one more question is, can you say anything about the case when the weight rho is not sign definite?
So can change sign?
Yes.
So the short answer is that I don't know, because then, so here I'm using that we have a positive first order elliptic operator. But this is a good question. So the short answer that I don't know, maybe we can leave it to at the end if other people can comment on that.
Okay, thank you.
You're welcome. So now when I start the main topic of our discussion, the mixed Steklov problem. And as I said in the beginning, by mixed means a Steklov-Dirichlet or a Steklov-Neumann. And our first result, the first improvement is when we look at the interplay between the Steklov-Dirichlet and the Steklov-Neumann problem. So the first result is that when we have a simply connected bounded domain, and we put, and then the boundary is two parts. One, we put a Steklov, and the other part I denoted by d star of omega. So it's the complement of this part. So either we put Neumann or Dirichlet boundary condition on this part, depending on which eigenvalue problem we take. And then the improvement is that if we take the minimum of this, the sigma k of Steklov-Neumann and sigma k of Steklov-Dirichlet, then here we can improve by -1. So in particular, sigma star 1 of omega times the length of the boundary is less or equal than pi. So the Weierstrass inequality was 2 pi k, and here it says that either a Steklov-Neumann or a Steklov-Dirichlet eigenvalue, one of them is less or equal than 2k minus 1 times pi, or for the first non-zero eigenvalue, at least one of them is strict, it's less or equal than pi. Moreover, if we have equality, then these two should be equal. So before giving you a few examples on which we can say which one is the minimum, let's very briefly talk about the idea of the proof. I skip all of the technical details, and draw.
So yes, Mark, can you show the previous slide just a few seconds more? Thank you.
Yeah, so here improvement in comparison to Hirsch-Payne-Schiffer result is replacing 2k by 2k minus 1.
Do you have to have that the star part is non-empty?
Oh yeah, yeah.
Okay, thank you.
Yeah. Yeah, but, yeah, the star part is always non-empty. Okay, so the sketch of proof, so the assumption is that omega, the boundary of omega is Lipschitz. So I simplify this assumption. So let's, for now, this is, I don't touch the Steklov part, the ds of omega. So I draw it smooth, but it's Lipschitz. For the ds star, I assume that it's piecewise geodesic. So here it's segment for segment. So I prove that the result for this kind of domain first, and then we can argue that everything can be reduced to this case. So here we have piecewise geodesic. So now let's attach 2 copies of this to each other. So we attach 2 copies of, so this is omega. We attach 2 copies of omega along this blue part. So blue part is a ds star of omega. So then we have this domain, we call it M. And this domain now has only, so if we consider the Steklov eigenvalue problem, so we have a boundary which is the length is twice, so it's 2 copies of ds of omega. So the boundary of M is 2 copies of the boundary of omega, and actually omega is M mod the reflection. If I call this union, if I call this part rho, M is has a reflection symmetry with respect to tau. So what we do now, we do a conformal change, preserving, we change the metric here. So we have metric, we don't change the metric here. So we have some conical singularity. So we change the metric conformally. So G prime is in the conformal class of G. We don't touch the boundary, the Steklov part of the boundary, but we get rid of all of the conical singularity. But at the same time, we preserve tau. So it means that after this conformal change, so it's the new tau prime. So now this blue line here, it's geodesic. So now we have a smooth manifold. If I look at, if I take omega prime to be M prime quotient by tau prime, then what we see here is ds of omega again. And here, this is a smooth, so it's omega prime, the new domain. And we know, so if you keep this picture in mind, so what we know is from the discussion that we had in the beginning, the Steklov-Neumann eigenvalue of omega is the same as a Steklov-Neumann eigenvalue of omega prime, because we didn't touch the boundary, we only do the conformal change. for M, if we look at the Steklov eigenvalue of M, this is the disjoint union of sigma k Steklov-Neumann of omega prime, and yeah, so this disjoint union with the Steklov-Dirichlet eigenvalue of omega prime. This is what we discussed in the beginning. So if I take sigma k Sn of omega prime and sigma k Steklov-Dirichlet of omega prime and look at the minimum of those, by a simple counting argument, this is less than 2k, so here m prime. The 2k minus 1 eigenvalue of m prime. So here you need to remember how we numerate the eigenvalue. We have 0 to k, which is k plus 1, and 1 to k. So in total, we have 2k plus 1, and here we have 2k. So at least one of them is less or equal than this one. And if we multiply, so if we multiply both parts by the ds of the length of the Steklov part, so this is equal to the length of the boundary of m prime divided by 2, and we use the Hirsch-Payne-Schiffer result, 2k minus 1 times pi divided by 2, so we get this upper bound. So we prove the statement for this type of domain when we know the Neumann part is piecewise geodesic. Any question? So what we do next, so for so we have omega is given, we construct a sequence of omega j, which uniformly converge to omega, and by uniformly, I mean in the sense of Bukur-Naun lemma. And omega j, we construct those omega j such that omega j is subset of omega, and the Steklov part of omega j is the same, so we don't touch the Steklov boundary condition, and the d star part of omega j is piecewise geodesic. So since we know that our statement holds for all omega j, then we apply Bukur-Naun lemma to pass to the limit. So here a few hand waving that I made is, so if the Steklov part is, so first of all, here when we do the doubling, we need to make sure that the resulting domain has a Lipschitz boundary. So we have to care about these angles here. And if this here is only Lipschitz, we may not be able to define an angle. And yeah, so there are some technicality that I didn't want to go to, but if you are interested, you can ask question now, or we can move on to equality part. Okay, so this is basically how we prove inequality. So now let's prove the equality part. So we assume that we have the equality and we want to show that these two are equal. So if they are not equal, then we have either of these two cases. So I prove that case 1 gives us a contradiction. The same argument, we can repeat it for case 2. So to get a contradiction, so now the assumption is that the case the Steklov-Dirichlet is bigger than sigma k of Steklov-Neumann. And remember that this is equal to, we assume that we have 2k minus 1 times pi over the length of the Steklov part. So we assume the equality. So we have this. So we construct a domain which contains omega, And the Steklov part of this domain is the same as omega. So here we use this nice monotonicity result proved by Banuelos, Kolczewski, Poltrovich, and Ciudea. So they prove that if we have if omega is a proper subset of omega prime, then we have these two strict inequality between these eigenvalues. So it's important that the inequality is strict. So in particular, for omega prime, the Steklov-Neumann eigenvalue, the Keith-Steklov-Neumann eigenvalue is strictly bigger than this, so strictly bigger than 2k minus 1 times pi over the length, right? So here we have this strict inequality, but we know that this one is already strictly bigger than, so let me write instead of repeating, 2k minus 1 pi over the length. Okay, so so now we can choose omega prime so that still this one, even though it's strictly less than this one, is still bigger than 2k minus 1 times pi. So then for omega prime, the sigma k star, which was the minimum of the Steklov-Dirichlet and the Steklov-Neumann eigenvalue, is strictly bigger than the bound that we already proved. So we get a contradiction. For the case 2, when we have this direction, so then we construct omega prime subset of omega and repeat the same argument. Any question so far? So now I want to mention one nice example. It's a family of domain which satisfies so-called John condition. So it's basically omega is a domain which lives in an infinite strip. So here actually we consider the sloshing problem because the Steklov part is flat. And here we have the Neumann part, and this is domain omega. So for this domain, the minimum is attained by the Steklov-Neumann eigenvalue, and this is thanks to the result in the same paper. So they prove a kind of Friedlander type inequality between the Keith-Steklov-Neumann and the Steklov-Dirichlet. Again, we start an enumeration of a Steklov-Neumann with 0, and here we start with 1. So, so we have this strict inequality, and in that case, we for this family, we have this inequality, and especially for sigma 1 of a Steklov-Neumann, the upper bound, this is strictly less than pi. And actually, this cannot be improved because if you calculate by separation of variable, you calculate the eigenvalue of infinite strip, then it approaches pi. But actually, this kind of bound is also true for domain that does not satisfy this. It satisfies a weaker condition called weak John condition, which it's not as geometric as this one, but yeah, so we can identify for those families what is the minimum between the sigma k of Sn and sigma k of Sd. So another family of examples that I like to discuss is domain with dihedral symmetry. And this will be kind of introduction to the next part of the result. So if we have a domain, so if we have two axes of symmetry orthogonal to each other, and let's assume that we have a domain which is symmetric. Okay, I'm trying to draw a symmetric domain, which so this is omega. It's symmetric with respect to these two axes, and if we put a Steklov boundary condition on the whole domain, so let me call it M, and so this is M, and half of that, this part, I call it omega. So again, because of the reflection symmetry that we have, so we can again write have a basis of eigenfunction which are symmetric or anti-symmetric with respect to each of these axes. So, and we can see that the first eigenvalue actually has at least multiplicity 2, because we have this reflection symmetry and also this rotation symmetry. So maybe I'm a little bit fast here. So if we consider so what I wanna say is that the sigma 1 Steklov-Neumann of omega is equal to sigma 1 Steklov-Dirichlet of omega, and this is equal to sigma 1 of m because of the reflection symmetry and rotation symmetry that domain has. So I wanna just quickly pass over that. So here the result that I wanna mention. So if we have a dihedral symmetry, then if we look at the quotient, so here I denoted by O because if we have a domain quotient by reflection, this is a stand for Orbi fold or Orbi surface. So then the first Steklov eigenvalue of this O is the same as sigma 1 Steklov Neumann of the underlying space as a topological space on the underlying space when we put the Neumann boundary condition on the reflector edge. And the equality attains if and only if when it's isometric to the half disk. So this quotient by a reflection. And this argument, so it doesn't need any, so we don't need the domain to be simply connected, so we can apply to any surface with any number of boundary component and improve the bound of 8 pi to 4 pi for this Steklov-Neumann problem. So again here, the Steklov problem and this quotient space is the same as a Steklov-Neumann problem when we put the Neumann condition on the reflector edge. You may ask why we assume genus is 0. We don't need actually, but we don't get any improvement because when we double, I mean the genus double, so it doesn't give much improvement in other cases. So in these two cases, we have sharp bound of 2 pi and 8 pi. So in this example, we see that we can improve these bounds. So interestingly enough, it was a theorem by Bandel that studies this domain. It has some symmetry. So it's not dihedral symmetry, but the rotational symmetry of order P. And she proved that the weighted Steklov problem, if we normalize it by weighted length, then we have this improvement of Hirsch-Schiffer result for K between 1 to P minus 1. And we have equality when omega is unit disk. It's not if and only if statement. And for K equal to P minus 1, actually the result was previously proved by Hirsch-Schiffer in the same paper that they proved there's inequality for simply connected domain. So as a corollary, if we add to this rotational symmetry, if we add a reflection symmetry which passed through the origin of symmetry, so a corollary of Bandel result is that if we have a reflection symmetry which passed through the origin of this rotational symmetry, so omega has a rotational symmetry of order P, then what we have here, so we can show that sigma k of O rho is less or equal than sigma 2k of its double cover. And then we apply Bandel result. And because the length of the boundary is half of the length of omega, we get this inequality. So it's quite a straightforward consequence of Bandel result. But one thing that it's interesting, and we didn't see that it has been discussed, is the sharpness of this interval, this range of K. Can we improve this if we have this p-rotational symmetry? Can we extend, so does this inequality holds for K bigger or equal than P? And the answer is no, which is a statement of the second theorem. So for K is strictly bigger than P minus 1 or bigger or equal than P, this inequality is sharp. So here it's not a complete list, as you see. We can add more to that list, but we cannot cover, so the construction that we gave to prove this statement, it doesn't cover all K. So it's interesting to show that it's always strict. And moreover, when K is equal to MP plus 1, when P is between 2 to 6, then we have the sharp bound, the Hirsch-Paine-Schiffer, so it's 2 pi K. So sigma K of omega is equal to 2 pi K. So here is so I start with the first part where we play with the Girouard-Poltrovich example. And for these two parts, also we modify a little bit the construction to get this strict inequality. And where we get this equality is actually where the construction is exactly matches the Girouard-Poltrovich example. So the idea for the first one is quite, so let me first show you the picture. It's just to put the disjoint union of disk or overlapping disk in a situation that they are p-rotational symmetric. So for example, here we put 3 overlapping disks together so that they are symmetric. So they have 3 rotational symmetry. And then when epsilon goes to 0, then they converge to that. And the 2 main ingredients of the proof, the first is this 2 monotonicity result. The first is when we have a partition of omega to some domain omega j, then sigma k of omega, if we have k partition, then sigma k of omega is bigger or equal than minimum of the sigma 1 of a Steklov-Neumann of each of omega i's. And this is a standard monotonicity argument. And the second is this strict inequality between the Steklov-Neumann eigenvalues when one domain is the proper subset of other domain. So this is the two main ingredients in this that we need to look at it when we consider this construction. So here is P equal 3. And so we are considering sigma 4 of this 3 rotational symmetric, which is 3 plus 1. So this is where we have 2 pi k equality. So the limiting, so the sigma 4 of omega epsilon, when epsilon goes to 0, is bigger or equal than sigma 1 of the disk, which is 1. And if we multiply by the length, of omega epsilon, the length of the boundary of omega epsilon, both sides, when epsilon goes to 0, then the length is just the perimeter of 4 disjoint disk, which is 8 pi. And we get like the sharp result. And the fact that we cannot go beyond 6 because the maximum number of disks that we can put around the disk is 6. I mean, for the P equals 6, we have to be careful to not lose the simply connectedness, so we don't get overlapping for 2 disks that are attached to each other. But this obstruction here, this 6, is because the maximum number of disks that we can put around that to create this rotational symmetry is 6. So for example, and when we consider MP plus Q, so here for sigma 7 still 3 rotational symmetry, we attach balls to this, right? So I didn't yet discuss K equal 3, K equal 5, and so on. If Q is 2, 3, or other, we take one of the disk, it doesn't matter which one, we just divide them. So for example, here I take a 4 rotational, so the symmetry of order 4, and now we consider sigma 7 here, so we need to find 7 partition. So 5 is already given, so I want to make it 7, but keep the 4 rotational symmetry as well. So I don't change the picture so that the picture is symmetric, but what I do, one of the disk, I just make it to 3 equal sector. And then the pieces are either, when epsilon, this is epsilon, this is where goes to 0. When this goes to 0, it is then the partition is either like a disk or this one. And if we calculate the first Steklov-Neumann eigenvalue, so blue part is always where we put Neumann. This is strictly bigger than 1. It's equal to Q over 2, and Q, it's always bigger than 2, so bigger or equal than 2. So the minimum between these two is 1. Again, we multiply by the perimeter and we get the bound. So remember that for Bandel, upper bound was times the length of omega. We want to show that this is bigger than K pi if K is even, and K plus 1 times pi when K is odd. So we want to show this strict inequality. And this is the case. So this is how we do for P between 1 to 6. So when P is bigger than 6, what we do, we draw a polygon of side 1. So here is trigon of side 1 or side 2, because I want to attach a disk of half disk of radius 1. So the polygon is of size 2, and I attach the half disk of on each. So we have this ice cream shape here. So when this epsilon, and we put, and the partition, it's how we show here. So this is our partition 2. And this part goes to 0. This is our epsilon. So any question about the construction, or I'm too fast? So when epsilon goes to 0, then we need to understand the first Steklov eigenvalue of disk and the Steklov-Neumann eigenvalue of C, this sector. So this sector, it has this half disk as a proper subset. And then here we use that one. We don't need to calculate for this sector. We only need this half disk to know the first eigenvalue of half disk. So again, the minimum is 1, and we will see that if we multiply by length, we have this strict inequality. We can do some, so for example, if remainder is 1 or 2, for example, we can divide one of this disk by 2 disks, or so the list that I gave you, it's not complete, but the construction doesn't cover. The main point is it does not cover all K. So far we cover K equal MP, K equal P when P is even. So when P is odd, for example, if you remove this disk, so for P equal 3, if we look at the center one, which we have 3 partition, the upper bound will be 3 pi, not 4 pi. So this construction doesn't give the contradiction. And for this, we actually can use some numerical result, nice numerical result due to Ahmed Galiev, Kao Austin, and also Bogosel. So they studied a numerical maximizer for a Steklov eigenvalue under area constraint. And they show that the maximizer, so here, this is a page of the paper. I hope that the images, it's visible. So this is the maximizer, but not for the problem that so the normalization is different. The constraint is area. So they prove that the domain they have, the maximizer has p-rotational symmetry plus a reflection. And they calculate the first 101 eigenvalues of this domain. So if we fix the area, I mean, this product is scaling invariant. So let's assume area is pi by isoprometric inequality. So this is, if the area is pi, the perimeter is at least 2 pi. So if we calculate 2 pi times that times sigma k of this maximizer, and it's strictly bigger than the Bandel upper bound, then this is what we want. So actually here in this table, for sigma 3, sigma 5, and sigma 7, that was not covered by our construction, the numerical result shows that we have a strict inequality. So since I'm going over time, so I wanna conclude with this conjecture and this open question. So the conjecture is that we have this strict inequality, so the Bandel result cannot go beyond this interval of k. But more interestingly, can we show that actually for k bigger or equal than p, the Hirsch-Payne-Schiffer result is still sharp? I mean, it's not trivial how to construct a p-rotational symmetry which converges to the disjoint union of disk. So, I mean, only in few cases we have this equality, and yeah. So I had 2 slides about higher dimension, but I want to skip those, and thank you for your attention.
Thank you very much, Asma, for the very nice talk. Are there any more questions? Any questions from the public? Please go ahead. So I had one question, but I mean, it's a bit strange. I wanted to ask you about higher dimension. So I don't know if you want to show the slides.
Okay, thank you. So in higher dimension, so this, the improvement that we've got, so in some of this, the conformal deformation is, it's very essential. So so if you ask about the first theorem, so the argument does not go through in higher dimension because we don't have this conformal invariant for Steklov eigenvalue. But again, if we restrict to either a sloshing or domain with some symmetry or like orbifold setting, we still get some improvement. For example, if we consider a sloshing problem, there is a result. So with Ari Laptev, we proved a kind of Kroger type result upper bound for the Steklov-Neumann. So the sloshing was the one that the Steklov part is flat. And the same also if we put, so this is the Steklov part of omega, and this is the Neumann part. So here we have a kind of sharp asymptotic for the average, which we don't know if we just look at the mixed Steklov-Neumann problem. And the same also for Steklov-Dirichlet, we get this lower bound, which is kind of a Liao type lower bound for, so this result we had it for Laplace eigenvalue, and this is the extension when we consider the this sloshing part, and the flatness of the Steklov part actually helps to use the Fourier transform and consider the test function that gives us such result. And for example, if we consider the orbifold setting, so this result that we had, so so orbifold is locally is manifold. Locally looks like Rn mod some isometric group, like discrete isometric group, which and we may have a non-trivial isotropy. So we can extend some previously known result to orbifold setting, but it's interesting that when we consider orbifold setting, we can see some sharpness. For example, we saw before that the power of this isoperimetric ratio cannot be is sharp from below. Just looking at the example of an orbifold whose boundary is the lens space. But now we know that all of the exponents are sharp by your result with John. But here, I mean, it was interesting that orbifold setting gives us some sharpness. Yeah. So.
Thank you.
So
go ahead, John.
In the higher dimensional setting that do you know if there's any Kroger type inequalities for pure Steklov as well?
I don't think so. I'm not aware of that.
Mm-hmm. So there was a question in the chat from Sheikh Sek who asked, is the Steklov-Neumann or Steklov-Dirichlet decomposition of the border possible in the case where the border is not smooth?
Oh, throughout the talk, the border is, the boundary is Lipschitz. So we don't assume, so we cannot decrease the regularity from being Lipschitz because otherwise we may not have discrete eigenvalue, but we don't assume the smoothness. Yeah. But you can always work with a smooth boundary thanks to Bukur-Naun result. So it's, you do the thing that you can do with piecewise a smooth or a smooth, and then you use that lemma too.
Does anyone else have questions or comments? So thank you very much, Asma.
Thank you.
Very nice talk.